Welcome to the Power Airwaves, the Power Manufacturing Solutions podcast series where we talk about manufacturing issues that impact you. Welcome to another edition of Power Airwaves podcast. Tell you what, before we go any further, I want to make sure that you understand that you can watch this podcast. You can actually watch it on AirPower Live, on AirPower Airwaves, or at airpower-usa.com. You can also find us on YouTube and all the social media channels, Facebook, Instagram, LinkedIn, Twitter, all of the above. So, you need anything, think about anything while we're going through this episode of the podcast. If you have questions, you can email me, Travis, at airpowerairwaves.com. Or call us at the 800 number, 1-800-334-1001. All right, this is a first of a kind for us. Most of the, or the only podcasts that we've done so far are one-on-one interviews. So today, I have 3 guests. So there's 4 of us here, all mic'd up and ready to go. And today we talk viscosity. Some of you are going, what's that? And others of you are going, oh yeah, I know exactly what they're talking about. We want to get everybody kind of on the same playing field by the time we get done here. My guest today, first of all, I'm joined by one of my colleagues, Peter Coulson. Peter is application specialist.
Yes, sir.
With AirPower. And Peter, you're out of Virginia, right?
I'm based out of Virginia and handle Virginia, West Virginia, Pennsylvania, and Maryland.
Okay. So you do a lot of traveling too.
Yes.
Yeah, you and I both fit the bill there.
Right. But we support all the account managers in the area, which
So you,
I have 8.
So you're in multiple different avenues though. You're dealing in finishing,
Finishing, sealing, and adhesives. Any process that you need to move a fluid from point A to point B.
Okay.
That's my avenue.
Perfect. So you're working in tandem with the account managers in that region, which we call East at AirPower. So you're working with that team. So I appreciate you joining us today, and some of your input is going to be highly desired in a little bit. I'm going to turn it over to our guests today, who are down here all the way from Michigan visiting us in our studio here in High Point, North Carolina. I have Ian Porzondek.
You got it. You nailed it.
Yes. Ian, tell us about your name, your title, where does the name come from?
Yeah, it's actually Polish, so the way you said it is the proper pronunciation. But
Porzondek
is
what
most go by. But
to be honest, I was coached a little bit, so
you might have been.
Thank you.
But you nailed it.
But it works for me. So what is your title with?
So yeah, I'm with the business development group at St. Clair. Started at St. Clair in November 17. And you nailed it. We're right out of Detroit, so about 35 minutes north.
Okay. Love Detroit. I have we were talking a little bit earlier. That city is dear to my heart. I have some fond memories there. Especially, no shock, the Pegasus restaurant, Carl's Chop House, the new Parthenon, and I can continue. All good stuff. Who's this person next to me?
Fair question. I'm Mike Bonner. I am the Vice President of Engineering and Technology for St. Clair. Been with them since January of 1987.
So all the tough questions roll down to you, or get pushed up.
No, always down.
Both ways.
I know what the bottom of the hill looks like.
All right. I want to talk about, let's talk about your company a little bit. They get enough of us on podcasts and videos about AirPower. In general, Air Power, we are, I don't even know how many states anymore, but basically Pennsylvania, New York, Maryland, all the way down to Florida and over to Mississippi. We're all in the southeast and up to the eastern seaboard, and also in Mexico. So we've got a nice footprint. For us, we break our products down into three main groups. You can see here: assemble, move, and coat. Assemble is the precision fastening, the tooling, the putting things together. Move is fluid transfer, material handling, and a lot of this falls into what we're talking with today. So today would definitely fall under move. And then coat for the coatings processes, which actually you guys have a lot to do in that market as well. So they know enough about us. Let's talk about your company. Give us a little bit. We know you're based in Detroit, but give us the quick snapshot, I guess.
We have focused over the last 30 years on the science of controlling viscosity in fluid dispensing operations. We control everything from low viscosity fluids, solvents, water, down 1 centipoise and lower, all the way up to high viscosity adhesives like windshield urethane, which is over 1 million centipoise. You can literally take the lid off the drum, stand on it, not leave footprints, and then you're expected to pump it over to a robot and dispense it. So we cover the whole gamut and a wide variety of industries, aerospace, automotive, medical, printing, food packaging, pretty much you name it, we've done it over our time. And as a result, we've got over 3,500 active installations today as we sit here.
Oh, wow. That is a lot. I know that there's a lot of questions. So I'm going to start this out. Now that we know who we are and have introduced ourselves, I'm going to ask this question. What is viscosity?
Viscosity is the resistance of a fluid to flow.
Right. Okay. So let's talk about that. Let's talk about how we see that in the real world. Like, how do we see that in everyday life?
Okay. You see it in the world around you all the time. Start with water.
Okay.
Okay. You don't think about a glass of ice water as being thicker than a cup of coffee.
No, I just know when I spill them, they get everywhere.
They do. But you see it in other fluids too. Think about honey. Okay.
All right.
If you take honey and you place it in the fridge, it gets really thick. So thick you almost can't pour it. Now if you take that same honey and set it out in the sun on a warm day, it'll thin down and it'll get so thin you can pour it almost like water.
Okay.
Okay,
So
now the difference in the way that it pours is the viscosity of the fluid.
So you went kind of extremes, right?
Right.
But if you take it and you put it in a cupboard that's a little cooler, it's not a refrigerator, it's not outside, now you've got a viscosity that's somewhere in between.
It is a continuum.
Yeah.
Okay. It's not, in general, when you look at temperature versus viscosity, it's not a straight line. It's a curve. It's an exponential function. But
Okay.
it is a continuum. The colder it gets, the higher the viscosity. And the warmer it gets, the lower the viscosity.
Okay. All right. Let's talk about that other one that we were laughing about it before we got started with the podcast. The other example that we've used probably 10,000 times in our lives.
We were talking about the difference between rheology and viscosity. And we were talking about thixotropic fluids. And Peter brought up thixotropic fluids, which most of the fluids that we deal with in industry are thixotropic fluids. And what that means is that they shear thin. As you apply force to them, they fall in viscosity. And we use the classic ketchup example. And if you've ever walked into a restaurant, sat down, you open the bottle of Heinz ketchup, you turn it upside down, nothing comes out. Now if you take that same bottle of ketchup, put the lid back on, and just shake it a few times, and then open it up, it'll pour out probably faster than you want. And The reason is you've put it under shear. When you shook it, you sheared that material and the viscosity fell. Now the neat thing about that is it has a recovery time. So I set it on the table, I finish my French fries, you come in, sit down at the table, and you order French fries, and you pick up that ketchup, and you open the bottle, and you hold it upside down, and nothing happens. We're right back where we started. It recovers that high viscosity when it's no longer under shear.
That's really interesting.
A couple of different ways of looking at viscosity.
So let's talk about some other everyday things that we see. We all go to the gas station. We all have work done on our vehicles, right?
Well, now we're talking about Newtonian viscosity. And everybody knows, well, most everybody knows, Newton originally came up with the concept of viscosity.
I'm related to him, by the way.
Oh, that's cool.
Yeah.
I thought so by the
I don't have this part of it, but no, we are our family lineage. My mom is a Newton, and so
Interesting.
it goes back like 6 or 7 generations, and he obviously didn't have kids, so we're not direct from him, but there is a lineage back to his family.
Well, cool. Well, he originally looked at fluids, and he didn't understand thixotropic fluids at the time.
Okay.
But he looked at different fluids, like honey. He realized that you could measure the resistance to flow. And he also realized that there was a relationship between temperature and viscosity. Okay. Now, you started to talk about oils and greases and that kind of thing. And those are Newtonian fluids. They do not change viscosity as a function of shear. Oils and greases are a great example. Water is another one. It doesn't change viscosity as a function of shear. But oils and greases are important because if, as you place them in shear, they started to break down and get thinner, they wouldn't be able to do their job, which is separating metal parts so they don't wear.
Okay.
So you want those to stay at a consistent viscosity independent of shear. They'll still change viscosity as a function of temperature.
Right.
You know, start your engine on a cold morning and it just doesn't want to get going. And they're better now than they used to be back when I learned to drive. But as the car warms up, well, then it starts to run a little smoother because the liquids move better. All of this is because of the relationship between temperature and viscosity of those
Gotcha.
fluids.
All right. And I mean that's gonna really impact manufacturing when you have a plant or you have an area that it's not heated or AC, and you get those winter cold drops and the heat. We see that in the paint side of the business. I know. Let's talk about how viscosity is observed or seen in the manufacturing sector. Where do we see this at? And I know we went over a couple lists. I don't want you guys to have to think about everything, but let's talk about some of these lacquers under the paints and coatings umbrella. So lacquers, water-based, solvent-based paints, UV paint, medical-based coatings. We've got a number of different things that fell under paints and coatings.
Yes.
So if you
Well,
need or don't
there's
be
a
shy.
lot of times the rule of thumb is that everybody gets these. They call them viscosity cups,
Okay.
and
Yes.
they're coming from a 5-gallon pail or a 55-gallon drum or a day tank, and the coating supplier is saying, "I want this product at this viscosity," so they'll take this cup, dip it down, start a stopwatch.
Yep.
Okay, and say, okay, it took 15 seconds to empty that little cup. Now I'll go to my chart, and 15 seconds in a number 2 Zon cup, this is my viscosity.
Number
Well,
two's on
the
cup, that's right.
guy on second shift comes and does it, and he does it a little bit different. Okay, because he might have lifted it out and he didn't start that stopwatch, and now instead of getting 15 seconds, he gets 20 seconds. All right, the coating manufacturers wants this at 15 seconds. So what am I going to do? I'm going to put some solvent in it to thin it out. Now I've changed the viscosity.
But you've also changed some of the characteristics of that paint.
You changed
So,
the formulation.
We were talking about, the formulation is somebody else's brainchild, and it's built to be a specific thing. And now all of a sudden you're messing with it for the sake of viscosity and adding in solvent, which is going to affect you somehow.
Well,
It never ceases to amaze me how we work hard with our coating suppliers to develop the perfect formulation. Okay, it's got the right adhesion, it's got the right film, it's got the right color, it's got the right gloss. Everything about it is perfect. And we get that all worked out, we've got it all set up, we bring the drum in, we open it up, and as Peter said, we dip in a cup, we measure it, we start dumping in solid, changing that carefully crafted formulation forever.
I know.
And then when it doesn't perform the way that we expected it to perform, who do we call and who do we hold responsible?
Air Power, St.
No,
Clair.
usually the coating supplier. So,
And the other side of that too is, so you've got the coating supplier that's made the perfect formulation. They ship it to the end user. End user has this coating that they would like to apply, but they've stored it in an area where it's too cold.
yeah.
Yep.
So now they bring the drum in, and instead of putting the additive to actually help the coating, they're only trying to put an additive because they need to move it.
Right.
And it's too thick for them to actually move. So they've created a problem. You know, they've added a problem basically to their process. So like you said, now they're adding solvent just to move it, and now the formulation's changed. And of course, it's not going to go on the part the way that they want to. It's not going to look. And like Mike said, they got to blame somebody, right?
Yep.
So
And we're going to talk about how to overcome some of those here shortly, but I want to get into another category to discuss a little bit. That was paints and coatings. Now we want to talk sealers and adhesives. So when we talked about this ahead of time, we talked about caulk, underbody sealer, glues, epoxy, foam applications. So let's run down through those a little bit and where we find those types of situations. I know that with caulk, you can see it on a number of applications, but large rig manufacturers will use that to seal up the cabs, and then based on whether they're powder coating or liquid painting or whatever they're doing, they have to have a caulk now here we talk about highly engineered stuff, right? A caulk that can withstand a 400 degree oven where they're going to cure that top coat that's going on it. So you can't just add solvent to caulk.
That's true. But you want that caulk to perform in a certain way.
Correct.
You're thinking of caulk like a bead. Okay?
Right.
Adhesives are the same way. Say that I'm going to put two products together. You're talking about sealing a joint between, say, two metal sheets. And it's a great application.
So like a 2-part epoxy type component
Exactly.
sealer.
But you might also have an adhesive where you're gluing two parts together. When you put down that bead of glue or sealer, you want it to go in a particular area, and you want that bead to have a specific profile. It's got to be shaped a certain way. If it's too tall, then it's going to squish out all over the place. It's not going to stay where you want it. If it's not tall enough, it's not going to join between the two parts and give you the strength or the sealing properties that you're looking for. So it's extremely important that it be dispensed at the right temperature so that it goes where you want it, in the volume that you want it, and stays where you put it until the operation is complete. And that operation might be gluing two parts together. It might be sealing a part, going through the oven and actually curing to seal the joints on a tractor trailer like you were talking about.
Perfect.
Because there's a lot more applications now where we're using sealant and adhesives for joining two parts together instead of using screws
True.
and rivets, because they've come up with so many different formulations in adhesives and bonding agents that can do this.
Right.
You
Well,
know, you look at a
bonding
piece of particle board where it's a bunch of
Little pieces.
yeah, well, it's just a bunch of shavings
Yep.
that they put adhesive in, and they pressed it, and they baked it, and it cures to a piece of particle board.
Yep.
And there you've got homogeneous materials. Adhesives are used a lot now as we get into all these various materials, composites and plastics and metals and different alloys, and now we've got all these dissimilar materials that all have to be joined somehow.
Yep.
And it isn't always good to use mechanical fasteners,
Right.
screws, rivets, etc. Adhesive solves this problem, but again, it comes with this whole list of other things. It's got to be there in the right volume. It's got to be in the right area. I mean, if you put it down and it slumps out and it's no longer where it belongs, it can be not only a strength and bonding issue, it can also be an aesthetic issue.
Yep. Well, I mean, when you use a mechanical fastener, you can undo it. You can take that back out. And when you're using some kind of a liquid or whatever sealer, a lot of times you're not getting it apart. It's
Right.
going to stay there, or you're going to do some major damage getting it apart.
And so to not create scrap, you have to control that process very tightly. So sometimes people get focused when they start talking on just paint or whatever, just sealer. But this applies across myriad different industrial applications. And fluids are becoming more and more prevalent in industrial assembly operations every year.
Well,
which is great.
let's talk about that. I'm going to segue us into this next section. So we've talked about like places that you see it in manufacturing, places you see it in everyday life. Why do we want to control viscosity? That's what I want to talk about. The value of controlling, value from controlling viscosity itself. You know,
Yeah, I mean, there's
what's our benefit?
There's different reasons, right? I mean, you have dispense applications where it's about quality. You're using expensive materials, whether it's a coating or a sealer. So if you're using too much, more than you need to, you're costing yourself. It's waste. Other avenues, such as if you're filling transmission axles or engine, and it's too cold and you can't move the fluid fast enough to fill as many units as you need to in a day, now you're talking about throughput. Or you're talking about not being able to expand your business and you're capped out because your bottleneck happens during the wintertime when it's too cold out and you can't move that fluid.
So basically, there's some that we had written down, cost savings. That's the waste and whatnot. But this was interesting, less operator involvement. So if you have a different person and you run 3 shifts and you have 3 different people running that same application, and everybody, I think this is true in every mode of manufacturing. You take 3 people to do the same job over 3 different shifts, and all 3 are going to do it differently.
Correct.
They're going to set the gun different.
Absolutely.
They're gonna set the line speed different. They're gonna touch everything. So having less operator involvement and more automation, you might have somebody overseeing to make sure when that red light goes on and you have the alarm goes off and you need to check something, but the actual function stays consistent.
And consistency is key.
Consistency was the next bullet.
Yeah.
Well, it goes back to what Peter said. Just take that one application. We're going to measure our viscosity with a dipping cup,
The Zon
with a
cup.
Zon
And a
cup number
stopwatch.
2, and a stopwatch. All 4 of us go take a measurement. We're all going to get a different measurement.
That's right.
But not only that, when we go to add how much solvent, Mike's been doing it 30 years. I'm the new guy. He's trying to train me. He might know just how much to pour in. I'm the new guy. I don't quite understand the importance because all I've been told is, hey, this needs to be at 17 seconds. If it's not, you do this.
Yeah.
I don't know why, though.
And at what speed of drip out the bottom of the cup are we supposed to actually stop at?
Right.
You know what I mean?
When it breaks, am I holding on an angle?
So yeah, consistency is a huge factor. Consistency, will also when you talk about that, will allow the line, the manufacturing process, and the line to put out the same thing all the time. Now, you can be consistently great, consistently average, or consistently poor, and so you really need to. The more things that you can put in place, the more checks and balances you have on your process, the better you're going to be.
And the other thing is, if we can control that viscosity with temperature as close to point of use of the dispense or spray or whatever application it is. We're taking one variable out of the whole scenario. We know we have a consistent
Correct.
viscosity going to that dispense head. Now, if something else is failing, then you know that it's not my viscosity. It's something else. It might be mechanical, it might be operator, it might be a production supervisor saying we need to increase the speed on this line from 15 feet per minute to 17 feet per minute. Well, you do that, other variables have to be changed too.
Yeah.
So, but we're taking that one variable out of the situation if we know it's constantly at a certain temperature.
Well, Peter, you make a really good point because you mentioned point of application, which is our claim to fame. It's what separates us from all the heat exchanger manufacturers in the world. Because we came to understand a long time ago, just like you pointed out, what's important is not the fluid in the drum or the fluid in the warehouse. It's the fluid I'm about to dispense on my very next part.
Correct.
And that's what's really important. And yet, how do we approach control? We approach it by temperature conditioning our warehouse or the booth that we're dispensing in, and we pump it from one area to another, and maybe it goes up to the truss level where it's 130 degrees in the summer and 65 degrees or lower in the winter, and we pump the fluid through there. By the time it gets to the point of application, it can be very, very different. And when you change temperature, you change viscosity. And when you do that, you change performance. So it's key to control, not in the warehouse, but at the point of application. I'm really glad you brought that up.
Right. But it's still, you have to still take in consideration where you store your material
Sure.
and all those components. But if you can get to the point, close as you can to the point of use, you know your viscosity there is controlled.
Correct. You had touched on something earlier that I wrote down. When we were talking about the value from controlling viscosity, and I want everybody to understand this, it allows you to make your fluid dispensing process predictable and repeatable. That's the everyday goal.
That's the mantra of every automation
Make
effort.
it predictable and repeatable, because if you can make it those, you can build around that to make it profitable.
Right.
That's the ultimate goal, right?
Yep.
So
You can raise your baseline, like Peter mentioned earlier. Hey, we want to increase our line speed. We want to increase our fill capacity. Well, if you don't know that your viscosity and your temperature is consistent, you don't know what it's going to be. You can't do those things to ramp up, your capacities.
all right. What kinds of defects are created by viscosity issues? This should get you guys talking very quickly. Again, for sake of not going down the crazy train rabbit hole, we got ahead of time. We talked about this. So basically, the randomizing of appearance defects is just, we get that. That's the randoms, right? Let's talk about orange peel.
Obviously, orange peel is a function of flow. A coating not moving the way that you want it to move. When the particles, say it's a spray operation, they hit the surface, they don't flow together properly, they don't become that smooth, even film that you're trying to create. That's really important. But that can be caused by the fluid being too cold and not flowing properly. That can be caused by the fluid being too warm and actually drying in the air and getting a dry spray condition where it hits the surface and it no longer has enough solvent in it to actually be liquid enough to move the way that you want it to. So it's really important to control the flow properties of the fluid and not just chemically. You've got the formulation that you created, but you have to dispense it under the right conditions so that it behaves the way that you originally predicted.
Protection and dispensing.
Correct.
Okay. Rivet
Rivet runs are an interesting one because you've got a dimple in the metal right there whenever you do that. And so you've got seams and cracks and crevices and all the things that are evil to coatings.
right?
Places to trap air, and also places that will automatically grab fluids and cause them to build up, but you've got different surface angles and things like that. So the fluid has a tendency to flow differently on the flat surfaces surrounding a round-headed rivet, for instance, and that can cause you a big problem.
Yeah, that's if you think about a rivet and a paint gun comes over and hits that rivet, it's going to build up on the top, and if it's not flowing correctly, it's going to run down the rivet to the bottom. So
Yep.
that's where you see a rivet run. It's not on the top; it's on the bottom side.
And that's assuming that the gun is spraying at a certain position. But even if the gun's coming from the bottom, you have a buildup on the bottom of the rivet.
Well, in most applications, no, because the way they're triggered, most rivet runs are on like a side of a panel. Okay, so they're spraying a flat surface, but they're hitting this, as Mike said, a dimple in here.
Okay.
Okay, and hitting a flat surface and a dimple is totally different. It's going to build up on that mound and make its way down.
Okay.
Here we're talking primarily about paints and coatings.
Yeah.
And this is just an advanced form of run and sag. And
Correct.
it's done because of the geometry of the rivet operation. But you see the same thing on regular panels, even when you're spraying in the flat. Or when you're spraying, for instance, in automotive. Think of the geometry of a modern auto body. And trying to get the paint to adhere and form a smooth, glossy, continuous film, and doing it across all these curves, and not just on the body itself, but also on the other parts. Think about a mirror. It's a deep draw part. It's plastic, not metal. You've got different substrates, and yet you want it to match the body exactly. So film is extremely important, and not generating visible finish issues like gloss issues and orange peel and all of that, and doing that on a really highly curved surface is extremely difficult. So this is why it's really important to control every step of the process. You control robotically, you can control the speed of the gun, you can control the distance from the part, you control the angle to the surface. From a flow perspective, you can control the flow rate and the pressure with regulators. All of these things are already controlled in the process, but all of them can create a problem. Now, it's nice in automation because you can repeat those things over and over and over again.
Right.
But you lose the one benefit that a human has, and that's eye-hand coordination. Because Peter can take a gun and he can spray and he can see how it's building up and he can adjust to that. He can play with the pressure regulator a little bit as he's going through the day and it's starting to warm up a little bit, and he can play with that pressure regulator. And he can make those adjustments. But a robot won't make those adjustments. It'll repeat those same motions time after time after time. So if it's creating a defect, it'll create that defect time after time after time.
Yeah. It's really perfect at making a mistake.
Indeed.
I saw a couple on this list. I'm going to go down through the list because I think it's fair to the folks that are watching or listening. The kinds of defects that are created would be like orange peel, rivet runs, sags. I was kind of surprised to see gloss and color there, but I think we're going to talk about those in a second. Dry spray and adhesion issues, blister defects, solvent pop, and too slow or too quick. So I get that. Those are all paint coatings type defects.
Yeah.
So I'm just curious on the gloss and the color, how viscosity affects that.
right off the bat, color is related to film. We talk about the hiding properties of paint, we don't realize how transparent it is. It's
Oh,
on a
yeah.
surface, the light's only hitting it from one direction. But if you put that on a clear film and you hold it up, you can see through it.
And you keep adding that solvent to increase your, to help with the viscosity, and now all of a sudden it takes more paint to do the job that you were doing before.
That's correct. And as, for instance, if you've added solvent, all of that solvent has to come out during the curing process. And that's really important, but as it's leaving the surface, it's disturbing the surface as it evaporates. And this is where gloss issues come in. This is where color match issues come in. Think about a metal flake. If you don't have a smooth, even coating where the metal flakes lay perfectly
Right.
flat in the way that you want them laying over one another, you'll get a real strange look to it, often referred to as mottle.
Yeah.
And so the way that the coating lays out, is it smooth, and can you build enough? If you add too much solvent and the viscosity is too low and you're trying to build enough film to get a good color match, you may end up running into run and sag because the coating itself is too thin and can't hang on the part the way you want it, especially in vertical orientations, in order to build that film geometry.
Okay.
We've seen the importance of this. You mentioned color, but we've got customers where it's not just about the solid color, but it's about the pattern. So lots of building materials are composite now. They've got patterns that look like a wood grain. So they're painting 4 or 5 different parts that are part of one structure. All of those parts aren't getting painted on the same day. Some might have been painted last month.
They have to all go together.
They all got to look good. And the coating process on the Friday at the end of the month when the one part was painted, if it's different, then all those parts are going to be rejected.
I know. I like to interject stories every now and then. I remember years ago I worked in the powder sided coatings for a long time, and got called by a customer who was actually the owner of a building in Florida that had windows on the front and the back of the building. It was an office building. So they were leasing it out to all kinds of businesses or whatever. And he said, I got a really weird phenomenon going on here. And it was like the building was a year old. And he says, I've got all these windows on the front of the building and they're all failing. And it was just a nice, extruded window frame. And then you go around, and they were all across the front, 2 stories. Go around to the back, they look beautiful, perfect. End of the day, we figured it out that it was two different coaters. One did they called it the male and the female. The male portion of the window, which was the bottom and the right side, and the female was the top and the left side. I think male, female, whatever. And the reason they did that is because they would lock in together. And I don't know why those are coated by 2 different plants. I really couldn't tell you.
Right.
But they were using the same RAL number, but it was 2 different coaters that were doing it. They were using 2 different vendors. And the colors matched and looked perfect when they were installed. But the UV, the sun was on the front of that building almost all day. And the back was in shade almost all day, just the way it was built. And so they were like, how does this happen? Like the ones on the front that had the one side and the bottom were just completely shot. So anyway, you talk about those things, you talk about control of your process is a huge deal. What I want to do is go in now, I'm going to switch this up into if somebody's watching this right now, and if you could talk to them about what they need to pay attention to, basically what happens if they don't pay attention to certain things. Okay, So this was a list that we all put together. What happens to solvent usage if they don't pay attention?
They're going to use too much solvent. They're going to, you know.
Bad to all that paint.
Well, it's inconsistent. They're going to use too much. We've been able to work with some end users. We're able to cut their solvent percentage 100%.
That's huge.
So by just using temperature. So, and of course we talked earlier too. It's not just about using too much, but you're going to add more than you. I might add too little.
So now we have a huge EPA, OSHA type positive environmental impact, which I could have other impacts. I mean, I'm not exactly sure, but it could have impacts with your insurance. It could have, with your safety in the plant. There's got to be a lot of positive impacts.
Well, there's operator exposure and that kind of thing. We actually worked with a coil coater on the West Coast and worked with them for a number of years. They were able to reduce their naphthalene additions to their coatings so greatly that they actually got an award from the EPA for controlling naphthalene emissions.
For being green.
Just for being good environmental citizens. And at the same time, they reduced the smell from the plant. They reduced what was going out to their thermal oxidizer. And so they reduced their costs. All kinds of things, all cascaded just from getting control of the process and just stopping adding solvent, bringing it in ready to use, and always using it the same, because no matter what temperature it is when it's in the drum, they know when it gets to the process, when it gets to the point of application, it's going to be at the right temperature, and therefore it's going to be at the right viscosity.
That's right. Now we talked about this one before, but I'm just going to reiterate it. Adding solvent to control viscosity changes the carefully crafted formulation, and therefore the performance of that particular paint or material indefinitely. You've now changed its ability to do what it was supposed to do. So, weather-related impacts. How does viscosity, if they don't pay attention to viscosity, how do they have some weather-related potential impacts?
Well, the big weather-related impacts is, we can talk about twofold. Waterborne materials, which have to be kept above freezing. Because any waterborne material that you freeze, you might as well just dispose of, because it can't be brought back.
Okay.
Okay.
Right.
Now, when you're shipping, you got to ship in heated trucks. You got to keep in a temperature-controlled environment. But we're going to get back to, this is all the prep before you get it to your circ system and everything. Everything's got to be done properly to get it to your circ system, and then you need to control it, because water-based is really finicky about, if you put too much heat on it, it's going to evaporate the water in the paint. Okay. So you're defeating the purpose of when you lay it out on whatever you're putting it on. Okay, solvent-based you don't have to worry about as much. Water-based is a problem. I want to go back to something that's really been prevalent these last few years, is in any kind of solvent-based materials, is we're going, in some of the shipyards I've dealt with, we're dealing with 100% solid paints. That means, like Mike said, you could stand on it and you wouldn't leave footprints.
Right.
You have to pre-mix it with a power mixer just to pour it into something, and you have to heat it. And once you get it up to about 110, 120 degrees, it flows. But I always use the thing with an ice cube, solid form. You put heat on it, flows like water.
Are these paints, when you say shipyards, I'm assuming Norfolk in that area.
Well, anywhere.
Anywhere, but those are typically used in the exterior of a boat or a ship.
Yeah, on metals, on bridges, on structural
Things
steel.
that are going to have a higher salt impact. So they're
we're talking, bridges, structural steel now. They're spraying structural steel with fireproofing now. So if it burns, they got a fireproofing cover on it, because that steel won't melt as quick.
Okay.
It's evident with our 9/11.
Yep. Absolutely, a lot of changes since then.
Right, exactly. So 100% solids, you have to put heat on it, and you got to keep that heat at a certain temperature for that material to flow. If you start off at 120 and 50 feet down the road, you got 80 or 90 degrees, that material's not coming out.
So, if you have that material that's hard to get moving and hard to transfer down the line to the gun or the applicator, you're slowing down your operations. So, simple ROI type analysis, you could probably help somebody figure out very quickly if they could get the line rolling every morning, get things up to speed, up to temp. You're going to be rolling wide open all day long with your process that beforehand you were pretty crippled.
True, but let's look at it even just a little bit finer down than that, because everything, Peter, you're saying is absolutely correct. But think about it from a process perspective. When you're trying to run, Travis, just like you said, flat out from morning to night.
I don't run flat out. We're all aware of that.
But if you think about it, your temperature is changing. Most manufacturing environments are not tightly controlled environmentally. It's just too expensive, especially in large buildings and that kind of thing. So your temperature is going to change just as sure as the sun is going to come up in the morning and set in the evening.
Correct.
Okay, the day that doesn't happen, you're probably not going to worry about your paint. But this is whether you're gluing body parts together or you're sealing seams or whatever you're doing, right up to painting and final assembling. All of those fluids that you're using are changing properties all day long. So as it gets warmer during the course of the day, they're falling in viscosity. And then as you move into second shift and that temperature starts to fall, that viscosity starts to come up again. So you're fighting this curve. And it's a curve that goes on from morning to evening, from day to day, and from season to season. So if you're going to correct for those weather effects, they're taking place in real time. You really have to counteract them, not just in the storage and delivery points, but then in the process point itself.
Good point.
You know, we've been talking a lot about coatings, but that adhesive sealer world as well. So we've seen applications such in Mexico. Obviously, we know it gets hot there as well as cold, but you can see the sealer actually falling off the part, right? It's too hot. Other applications, after the sealer's been applied, you've got up to 6 operators underneath the body of the car applying the sealer where it didn't get because the bead was inconsistent. So you talk about cost. Now you're paying 6 operators to basically touch up the job that the robots were supposed to do.
That could have been done easily.
Yeah.
In a controlled process.
Taking brushes and brushing it back where it belongs and spreading it out, making sure that it's where it belongs, that it isn't where it doesn't belong, etc.
So, what does the word hydropurge mean to you? money. Is that cost savings or is...
Hydropurge is an interesting topic because hydropurge works best at an elevated temperature.
What is hydropurge?
Hydropurge is used to clean guns or bells when you're using waterborne materials.
Okay.
Okay. And the hydropurge is usually a DI with an amine and other assorted chemicals that cause it to clean very, very quickly. Clean the cup on the bell or the nozzles on the gun, and it's fairly pricey material. If you can control that at the optimal temperature, you can increase its cleaning efficiency and you can reduce the amount that you have to use. You can shorten your cleaning times and reduce the fluid that you expend on each cleaning cycle. And those go on all day long. So that adds up in a hurry.
Yeah. All right. Is hydropurge more efficient at an elevated temperature?
Yes, absolutely. And they all have, you want them at the right temperature. well, if hot is good, hotter is better, right? Not true, because many of the aqueous cleaners actually break down at elevated temperatures. So you may want to run them in the 110, 120 Fahrenheit range. But when you get them above 130, they may start to break down, and then they actually get worse. And they're, as Peter pointed out, they may be separated and destroyed, and you can't ever mix them again. You can't ever use them again. You just have to throw them away. Not the optimal use of your cleaning solution.
All right. We talked about excessive paint usage. I think we covered that one. I have a word here that is, I want to get your description of. The word finesse. What is finesse, and what is the impact of finesse?
Finesse is, I think most people think of finesse differently. They think
Yeah.
of it as smooth and cultured, and when we say finesse, we're talking about buffing and polishing a part to remove defects after it's been manufactured.
So basically fixing the boo-boos.
Rework.
Yep.
In a word, it is a nice way of saying rework.
And rework can typically cost you 3 to 7 times the cost somewhere in that world. Everybody's a little different, but it costs you 3 to 7 times what it costs you to make it the first time.
It can, and especially if you have to go back and recoat.
Absolutely.
But the goal is to create shippable product. The goal needs to be to create shippable product as it comes off the
The line.
manufacturing line, not adding rework to the process, finesse, buffing, any adjustments like that to make the product shippable.
And that's a big part, but in some of the processes, there is no rework. It's scrap.
It's a good point.
Because when you do adhere to things with a bonding agent or adhesive, you don't go rework that.
No.
That's just scrap.
It's just loss.
It's loss. It's loss. And that's, how do you justify loss?
Yeah.
You can't. It's just scrap. You're going, okay, 80% of my product coming through is good, 20% I know is loss.
So maybe to the person who is running a manufacturing operation right now, and some of this is ringing some bells, and instead of just factoring in that loss into your daily, like, the plus or minus, we don't want anything greater than this loss per day, per shift, per whatever. Let's talk about getting rid of that loss and, putting out more uniform first pass parts every day out of the plant and just get more profitable from the get-go.
I don't know. I don't think there's a plant manager in anywhere that if you can't decrease their rework and scrap, that you cannot sell a product. And that's what a good ROI will show.
Now I'm going to talk about ROI in a minute.
But I'm sorry to interrupt, Mike.
No,
you're great.
Because first pass yield is usually one of the very first things that you look at for ROI, because increasing first pass yield is increasing throughput. That's putting more saleable product at the end of your line.
Correct.
With less cost. Anytime you're adding to the top line, instead of just subtracting an expense, and you're increasing the overall revenue of the operation, it changes the ROI equation very quickly.
Mm-hmm.
So we've talked about a lot, but I want to switch the gears into taking control of viscosity. This is an area where I think we can make a lot of impact in this conversation with those that are watching, listening. First thing I had on this list was control viscosity where it matters most.
Point of application.
Yep. So we're talking, you might need help getting it from here to here, but if the application's going on here, we want focus here first. If we need more assistance getting from here over here, we can deal with that. But point of application.
One of the things you must do is you have to get the coating or material supplier involved with all of this. It's very, very critical because you need to know what their parameters are for putting that product on the substrate.
Yeah, because maybe the temperature is important.
Well, yes, I can do it in a lab condition.
Yeah.
Okay, I can make anything work in a lab. Okay, you take it in the real world, you know what happens.
Yeah, all that fun real world stuff.
Right, exactly, exactly. So, getting the painting supplier, the sealant supplier, or whoever, to give you their parameters, then you have a starting point to go with.
Right.
Okay, and that's not parameters back here storing it in the thing. We want to know what you need at point of use, and that's where we have partnership with St. Clair in, and trying to persuade customers that's where you are critical.
Right.
I don't have, you might have a fluid heater in that mix room, and we're pumping it through 130 feet of stainless steel tubing. Well, what's the temperature out here? I don't know. It says it's 80 degrees back here in the paint room. I have no idea what is this back there.
Yep. All right. Viscosity is critical to automated paint system consistency. Well,
Actually, not just paint systems, automatic fluid delivery systems, be it paint, sealer, adhesive, lubricants, pottings, encapsulants.
beads of whatever.
Yeah, whatever. It's if you're delivering a fluid in a manufacturing operation, it's just as critical to have that fluid at the right viscosity as it is to have the right length screw when you're screwing two parts together. If your screw's too short, it doesn't work. Plain and
That
simple.
is true. We talked about manual adjustment, I think, enough before we did that. But we're talking about relying on eye-hand coordination and over the time skills that someone acquires to be able to looks okay. the intuition.
When you think about it, we talked about finesse. We talked about having, a number of people at the end of the line that really understand what fit and finish needs to be. These are skilled eyes and skilled hands. Same goes with a paint operator. Someone who's really talented at applying paint is a valuable commodity. You don't replace them with automation. You move them to areas where they can benefit your business better.
Right. That makes total sense. Okay. Robotic application will repeat the same motion time after time. We covered that. Let's get down to it. Let's talk about ROI. Is there an ROI calculator you can use for this type of scenario, this type of system?
Of course.
What goes into, and I also want to segue that with opening up the floor to you guys to talk about possibly recent collaborations with St. Clair and Air Power. And what I really am looking for there is, how did it happen? How did we understand, okay, here's an issue, here's a potential partner in the field. How did we make that happen together?
Yeah, so we had recently had a prospect reach out. They had a manufacturing process where they were spraying, but they had always done it manually. They
Okay.
were building a new facility. It was going to be automated. First time, they're going to have 2 lines. So they reached out, understood the importance of temperature and viscosity into their paint process. And since it was, they were new to the automated scene, they had all these different variables they wanted to maintain. So then being in the region where you guys are located, we wanted to collaborate with Air Power. So that Air Power would be able to provide the support needed, being very local. We could work together, offer our solution. Being that you guys assemble, move, and coat, it kind of falls in line with what we do. So the customer wanted to start with, they wanted to do a demo. they had two lines right next to each other, so they thought it would be great if they could put temperature control in one line compared to the other line that didn't. It'd be a pretty simple, decision to be made. So we collaborated with Peter, Brian Martin, who's the account rep. We worked using just a quarter of one of their lines. We implemented a temperature control solution as a demo. One of the key aspects, though, was to get commitment from the customer to work with us. That being said, they actually purchased part of the demo. So they've got an investment. They knew that we wanted to partner with them. When I say partner, we're going to work together. So it wasn't like we were going to just put the demo in and just let it do its thing and just let them, have at it. No, we actually met with them weekly. So Peter and Brian's team, our team, 5 individuals internally with the customer, which I thought was really key. So I thought the fact that the customer was investing in the demo, it meant that internally they had to all get together and collaborate as well for it to be a success. So we did. We spent, it was about 6 weeks overall, but like I said, we met each week to go over the results, what they were seeing. Peter can attest to other things that the temperature control actually showed in their line. Like we mentioned, they were new to the automated world. So there was a learning curve for them, not just in regards to applying the paint at a particular temperature, but also getting everything lined up with circulating the paint properly, the gun speeds and so forth.
Very good. So that's turned into an actual bona fide project installed and.
So like we said, the demo was a success, so much so that they purchased the equipment for the rest of the line. So not just the demo equipment itself, but the other booth. And they're most likely going to move forward with the other line as well. That's in the works, but just finished up the installation not too long ago, and we've got a happy customer with lots of results. And we were able to learn a lot too. Not just how to work with you guys moving forward, but I know Peter and Brian were able to learn more about how our equipment, can impact their end users.
Right.
We got to see firsthand,
how to integrate your technology in with what we're already doing.
Absolutely.
So, and vice versa, really. All right. Let's see here. Well, I think we've really talked, pretty much covered viscosity today. Do we want to talk about anything else specifically? Has anybody got anything on their mind they want to bring up?
Well, I want to bring up, not only temperature control, but St. Clair's does other things besides temperature control.
Let's talk about it.
And we were talking about your viscometer.
Yep.
If you can elaborate on there, y'all do more than temperature of material. You do other aspects.
Yeah, it's a really good point, Peter. We talk about controlling viscosity at the point of application, but control takes on a lot of different methods. Okay, and you're referencing our line of viscometers. Instead of measuring with a cup and a manual operator, we can automate the measurement process. Now, if we're trying to maintain a specific viscosity, I want this coating to always be at 220 centipoise. We can watch that, we can monitor it, and not just get a spot measurement when we opened the drum in the first place. We can monitor it continually throughout the day, throughout the process. And we can make other adjustments. We can modify it by controlling temperature. There are places where you want the temperature to be stable, but you're trying to counteract, say, evaporation. So you may automatically add solvent back to replace evaporation in a recirculating process. Coil coating is a good example where you've got an open tray of coating, and whether it's going on a polyethylene web or it's going on a steel strip or an aluminum strip, whatever you're coating, if it's in an open tank, it can be evaporating. You have to replenish those solids or your viscosity will shift just from solvent evaporation. And while you can compensate with temperature, you really want to maintain that formulation the same.
Right.
Evaporation can change that carefully crafted formulation too. We can counteract that. So Peter's right, there's a lot of different ways. We've talked today a lot about controlling with temperature because it is the primary way of controlling at the point of application, but there are other tools. And the ability to, instead of talking in temperature and inferring viscosity, we can measure viscosity directly and control directly in viscosity units.
Okay. All right. Anything else?
Just to add to that too, so we've had a lot of customers reach out. You know, in this day and age, there's so much information out there. And in the manufacturing process, there's so many different things that they need to monitor. So this is one more of those things. We've had a lot of requests. People want to know what their viscosity is. And they're not necessarily going to do anything about it, but it's another data point so that they can determine what is going on in their process. And they have a lot of different things to address, but now they can measure it real time. So now they have data. We talked before about the manual measurement. I had an end user that basically said they had 5 years of manual measurements that were useless because he watched how the process was being done. So they couldn't use any of that data. Not to mention this particular process, they were only able to measure 1 tank a day because they had 13 tanks. It took them a half hour to take it apart just to take one measurement. So you could see that they didn't have enough data to do anything with. So it's just another part of the process they can monitor. They can get all of the facts. Now they can move forward. They can make decisions. They can make adjustments to better automate that process.
Very good. All right, Peter. Anything else?
I'm good.
I think we're good. I think we've covered viscosity today. Learned a bit, I can tell you that. I want to thank my guests, Ian and Mike, with St. Clair. I really appreciate you guys coming in.
Thank you so much for having us.
You're actually coming in off of an install
We are.
with our team, with Peter and Brian over the weekend.
Mm-hmm.
So I wish you guys the best of safe travels back home.
Thank you.
Back home to Detroit. Eat some Greek food for me. I'm going to start closing it out here real quick. Appreciate you attending this podcast or listening to this podcast. I do want to say we've made some advancements here since our first podcast or two. We are now available through, or you can listen to Power Airwaves podcasts on several apps. You can download these apps on Android or Apple, on Stitcher, Apple Podcast, Spotify, iHeartRadio, and Pandora. So we're available on all those mediums right now. You can also watch this. If you're watching it, you can also do the podcast when you're in the car. If you're listening to the podcast, you found us. We're glad that you found us, and we would welcome you to visit us online. You can actually watch these podcasts. They're all filmed and recorded. You can go to our website, our official website for AirPower, which is airpower-usa.com, or visit the airpowerairwaves.com. That's air, A-I-R-P-O-W-E-R, AIRWAVES.com. And then the last one is the tried and true airpowerlive.com. We're available there all the way. If you would like to look at some things that we've done in social media, and pretty much all of these podcasts will come up on social media, please go to your favorite social media platform and look for us at YouTube, Facebook, LinkedIn, Instagram, Twitter, all of the above. And you can get links into our podcasts or our other training videos. We don't just do podcasts. Do a lot of training videos as well. Any questions regarding this video or other videos, or you got an idea for a podcast you'd like us to do or a video you'd like us to do, shoot me an email to travis@airpowerairwaves.com. And you can call 334-1001 and reach anyone at Air Power that'd be glad to help you. So remember, I'm going to close this out by saying manufacture it a great day.